Welcome to DCTP.tv from the Falling Walls Conference 2013 in Berlin. My next guest is Robert Kirshner, astrophysicist from Harvard. Welcome to the program.
Thank you.
So I read this little quote from you on the web saying, well, the universe is much stranger than we think. And then I thought, well, there's nothing stranger than the universe. I know. So it started everything with a Big Bang, right? This is still the idea.
Yes, that's what we say. We know that the universe is a very big place, and we have a way to see into the past. You know, a telescope is a kind of no-nonsense time machine, because light travels at the speed of light. Everybody thinks that's very fast, but to astronomers it's very slow. It's a foot. It's a unit we use in the United States. A foot in a nanosecond, a billionth of a second. So you'd never see the world the way it is right this second. You see it the way it was. Light bounces off you, I see you 4 nanoseconds ago. But if you're looking at more distant objects, the light takes time to get here. So across the room might be 10 or 20 nanoseconds. Just a joke in local distances. But for cosmic distances, we can see starlight that set out 10 years ago or 50 years ago from nearby stars. The galaxies that we see are millions of light years away, so the light's been traveling to us for millions of years. And the most distant things we can see are many billions of light years away. The light's been traveling to us for billions of years. But the interesting thing is, there's an upper limit to all of this. That is, as you look farther and farther back in time, you see a hot, dense glow in all directions, as if the universe were hot and dense everywhere at some early time. And that's the time we think of as the time of the Big Bang. It's about 14 billion years ago, when the universe was hot and dense, before the galaxies formed, before the stars formed, before there were any planets or any people. There was a hot, dense gas.
But how is it that you can still see it?
Well, the light has been traveling to us all this time. Now, there's a kind of fog bank that scatters the light. You know, the universe is more or less transparent. We can see light from far away, but there is a kind of cloud bank or fog bank that we think is about 300,000 years after the actual explosion event itself. So the Big Bang is the beginning of time, as far as we know.
But when my son asked me, what was before the Big Bang?
Yeah, well, you tell him you can't ask that question. The idea
there wasn't
is...
even time.
Well, probably not. I mean, that's a more philosophical kind of question that I know how to answer by making a measurement at a telescope. Nevertheless, the idea is that, time seems to be measuring the separation between events. And if there were no events, then maybe, time wouldn't really have any particular meaning. So, you can ask questions that seem like they ought to be sensible, but really aren't. If you go to the North Pole on the Earth and you ask, well, what's beyond the North Pole? Well, there's no real answer. That's where the coordinate system starts. And so this is what we think of as the beginning of time, anyway, in this kind of lowbrow, practical way that astronomers have.
So, and from then on, the universe expanded.
Yes, that the whole universe, not that you see, you were making it as if you're standing outside it and looking at it and there's a center. That's not the idea we have. But it looks like every bit of the universe was stretching out in all directions. If you think what that would look like from a vantage point at any place in the universe, you would see your nearby neighbors moving away from you, the distant ones moving away more rapidly. And that's what we see, okay? Astronomers measure the distance and velocity of the galaxies in the universe. And what we see, and what we've known about since 1930, is an expanding universe, one in which the distances between the galaxies are getting bigger over time.
And you measure it by light waves.
Yes, we can measure the velocity by we take the light, we break it up into a rainbow, a spectrum, and that spectrum gets shifted to the red if the galaxy's moving away from us, or to the blue if it's moving toward us. So we measure that, the redshift mostly. And then the distance, so that's the velocity. And the distance we get from the apparent brightness of some object whose brightness we know. So, for example, what I have been working on is using exploding stars, supernovae, which there's a certain class of supernovae.
1A, 1B, or?
Yeah, these are the so-called type 1A supernovae that have, well, not exactly the same brightness, but we can figure out how bright they are, truly how bright they are.
And then supernova means exploding stars.
It's an exploding star. It's a star at the end of its life where there's a sudden burst of energy where the star gives out as much light as 4 billion stars like the sun. So we can see these things very far away. And we've developed ways of telling which ones are a little extra bright, which ones are the standard brightness, which one's a little dimmer. And by doing that, we can judge the distance from the apparent brightness. You know, if you look out at night and you can tell whether something is nearby or far away, say the lights of a car, you can tell whether it's nearby or far away by how bright the lights appear. Yeah. So we do the same thing, except it's not car headlights, it's something much, much brighter, and we have very sensitive instruments to do this.
Yes. So one would expect, well, okay, there was an explosion, or however you want to call it, Big Bang, and the universe is expanding. Well, there's gravity, and somehow the expansion should slow down at least.
Yeah.
Because of gravity, and maybe one time it comes to a halt, and maybe the expansion gets negative expansion.
Well,
so what did you find out? How
the rules of the game are the rules of gravity, and those were thought out by Albert Einstein in his theory of general relativity. So that's about 1917. When he first applied general relativity, the theory of gravity, to the universe. And he thought the universe was static, not expanding or contracting. So he put in an extra term that makes the universe static. Gravity's pulling in. He put this extra cosmological constant, we call it, that would make the equation so that the universe would stay static. And he thought that was a great idea. But 10 years later, astronomers showed that that was not the right thing, that the universe really is expanding from these measurements that I've described of velocity and distance. So that's really interesting. Einstein said, oh, cosmological constant, terrible idea, don't talk about it anymore. And we thought, just as you said, that the universe would expand, slow down, and then coast out. And the interesting thing is that we began in the 1990s to try to measure that deceleration, that slowing down that you would get due to the presence of matter in the universe, mass in the universe. So we started to make the measurements, and by 1997 and into 98, we had enough of these distant supernovae and nearby supernovae to see that there was expansion and there was slowing down, but then most recently speeding up. So
speeding up, the expansion is accelerating.
Yes, it's accelerating. So this is very surprising, and we thought, oh, we must have done something wrong. We looked into it quite carefully and thought, no, this is for real. We're really seeing evidence that the universe is expanding faster now than in the distant past. So it has sped up in the last 5 billion years or so, since the formation of the sun, more or less, and the formation of the Earth. The expansion of the universe is speeding up.
How is that?
Well, it turns out you could have Einstein's cosmological constant, this thing that he said, oh, terrible idea, throw this away, don't think about it anymore. We have to go diving into Einstein's wastebasket, get this out, smooth it out, and say, oh, look, good idea. So it could be something very much like the cosmological constant. We call it the dark energy. That's a little broader term. It could be the cosmological constant, which would be an energy associated with the vacuum itself, with empty space itself. So you might think, empty space, that must be empty. Couldn't have any qualities, but not quite. In modern physics, there's this idea that if you look on very small scales, there could be fluctuations in the energy or fluctuations. The uncertainty principle tells you that. And it could be that there's properties to space itself, an energy associated with gravity that is something like the cosmological constant that's making this cosmic acceleration. Well, if that's true, we better find out. This is the energy associated with the expansion, the dark energy, corresponds to about 70% of the mass energy in the universe. So there's this invisible thing that we don't understand much about that makes up most of the universe. The stuff that we see, stars, galaxies, the stuff that we love, planets, I don't know, people, they're made of the ordinary matter, the elements of the periodic table, made of neutrons and protons. We kind of know all this. That only makes up 5% of the material in the universe. The rest is the dark matter,
25%.
Something like 25% that is present in galaxies, but it's not the stars. And then this dark energy that's making things fly apart. So our view of the world is this is a very strange picture for the world, in which the things you see are only 1/20th, 5% of the stuff that's out there, that the fate of the universe is decided by a kind of tug of war, a battle between the dark matter, trying to slow things down, and the dark energy, which seems to be winning now, trying to speed things up.
Because since you mentioned dark matter, it means it is matter we cannot see, but the matter itself is subject, for example, to gravity, right?
Yes, it's something which has gravity, but we have other clues that it's not made of the ordinary material like neutrons and protons, the stuff that makes up the elements that we know from chemistry. That it probably is some other kind of particle, which we know about, that interacts only by the weak force. So there are 4 forces in nature. There's gravity and electromagnetism. Those are the ones you know. There's the strong nuclear force that's involved in nuclear reactions. And then there's the weak force that's involved in radioactivity. And it turns out that's really well named. It's very weak. And you could have particles like neutrinos interact only by the weak force. So we know there really are such particles. The trouble with neutrinos, which are the ones we know about, is they don't have enough mass. So you need yet another particle. Well, if there's one thing that particle physicists are good at, it's imagining additional families of particles. So it's possible that in the particle accelerators here on the Earth, we'll get some clues to what those particles might be.
And what does it mean if the universe is accelerating its expansion?
Well, what it means is that if it's really due to this cosmological constant, the expansion will just keep on increasing, literally exponentially. So the bigger the universe is, the faster it will expand. And if that's true, then the future is kind of bleak, It means that the galaxies that we see will recede from us faster and faster until we don't get light from them. And it means that eventually we'll be more or less alone with our little neighboring galaxies. Maybe the Andromeda galaxy and ours will merge. Eventually there'll just be one galaxy and then a big, empty, cold, dark place out there. So this is why we must do this work now. We have to really get going and find out what...
Okay, but what does it mean for us? If we are still there when the universe, I don't know, is speeding up. Well, it's speeding up already, but what does it mean for us, for our worldview?
We're not at the center of things, is what it tells you in a kind of a brutal way. We're not at this. The Earth is not at the center of the solar system. The solar system is not at the center of our Milky Way galaxy. Our Milky Way galaxy is just one of 100 billion galaxies, more or less like one another. And what this is telling us is that all of those things, stars, planets, galaxies, people, all that stuff, is not even the material, the kind of stuff that makes up most of the universe. So I don't know. Maybe it makes us a little more humble. I doubt it. Personally, I think that the heavy particles, the baryons, really are the best particles, and that we happen to be made of the best kind of particles.
But how does it make you feel if there's only the matter we know is 5% of the universe, and there's 25% dark matter. We only have a rough idea what that might be, and then there's 70% of dark energy.
Right.
As far as I understand you, we know even less about.
That's fair.
And how does it make you feel?
Well, it might make you feel special, that we're part of the 5%. That would be good.
Okay, it's one perspective.
But I would say it's just a reminder that the universe doesn't really care what you feel, and whether it makes sense to you, common sense or not, it's not a really good guide to how things are really arranged. The common sense that you have, the sense of what's likely and what's unlikely, comes from living on the earth. You throw a ball and it goes up and comes down. But this is something where if you threw it up, it would kind of take off. So this is, it's not our common experience. It's beyond our common experience. But it's real. I mean, we measure this. We're not making this up. And of course, it's quite recent. It's only 15 years old. So that means we haven't had a chance yet to find out very much about the nature of the dark energy or the nature of the dark matter. Now, for the dark matter, there is the possibility of an experiment on the Earth where the dark matter particles, if they're in our galaxy, will be in the path of the Earth as it goes around our galaxy. And so there ought to be a mist of these particles, like a fog in the room, that we're going through at 200 kilometers a second. So people have built very delicate experiments, put them down in mines to get away from...
And?
They haven't found it yet.
Huh.
Yeah, not yet. But, it's very promising. And if we're on the right track, which is not guaranteed, for what kinds of particles they are, then the experiments can be designed to really look for this. So just last week, there was a report from the best of these new experiments in the middle of the United States down in a gold mine. And they didn't find any particles. So that was, in the one sense, a little disappointing. But it means we are going to have to look better.
But dark matter and dark energy is theory. So far, you haven't had an experiment proving that either one of them exists, right?
Well, I suppose you could say that. The astronomical evidence is quite strong that we see for the dark matter. We see the orbits of stars in galaxies. We can measure how fast they're going, and there must be a lot more mass than is associated with the stars that we see, because we know how fast they're going, and we know how much mass it takes to be in an orbit of that size at that velocity, and it's much more mass. So you could say, well, you just made that up, but that's how you find out what the masses of things are. You look at how they accelerate objects that are in orbit around them. That's how you would measure the mass of the sun from looking at the orbit of the Earth. So that's the kind of evidence for the dark matter. And for the dark energy, there certainly is this cosmic acceleration. We see that the expansion now is faster than it was 5 billion years ago. So that means something real is happening. Now, what you're onto is the idea that we don't have a good laboratory experiment. And I think the situation is a little like it was when astronomers knew in the 1600s that the speed of light was finite. They knew it took time for light to get from, say, Jupiter to us, because the clocks were good enough then that, this many minutes, 20 minutes or so, 30, 40 minutes of delay, they could really measure that. But you couldn't measure it in the laboratory because, it's a foot in a nanosecond, 3 nanoseconds for a meter, and the clocks weren't that good in the 1600s. So it wasn't until 1840 that people devised a very clever, very fast timing system to show that the speed of light was finite, measure the speed of light. So I would say it's a kind of a situation like that where the astronomical evidence is really good. We know we're right. I mean, we think we're right. But there's no laboratory experiment yet that shows it. That's why it's so promising for the dark matter to look for this direct interaction, and also to look in the particle accelerators to see if there is a new family of particles that could be the weakly interacting massive particles.
Well, the last part is, of course, when you say, well, we're not in the center of anything, and the universe doesn't care much about what we think and do, but and these are very, very fundamental and basic questions you are dealing with, right? And what is the answer that you give yourself when you ask yourself, well, who did it all make?
Well, I think it's very interesting that we're really just discovering what the world is, what it's made of. We didn't know about this 20 years ago. And, it's good. We should kind of find out what the world is made of, find out how it works. I think the questions you're asking, the questions your son was asking about how things begin, is something that's in the back of everybody's mind. And this is the modern scientific answer that we've seen more and more of how the universe works, what the forces are, how they play out over time. But it's really interesting because if this balance between expansion and slowing down were much different, then probably galaxies would not have formed, stars would not form, the heavy elements would not get produced in the nuclear fusion in stars, there would be no planets, there would be no people, there would be nobody here answering the question or asking the question. So we are learning something really interesting about why we're here, or not exactly why, but how we're here. And I think that most people have a deep curiosity about this. So this is the material world. It doesn't tell you how to be a good person, but it is a view of where we came from that I think most people care about.
Yeah, and is God in this equation?
Don't need God in the equation. You need the cosmological constant or something like that. But, it's not about religious belief. It's about a kind of description of the world that we're in. Now, what inference you would like to draw from that, that's sort of a separate thing. But, it looks to me like there are laws at work, the natural laws, the scientific measurement of which tells us, about the forces in the world and how they operate. But you're right, it doesn't tell you where those laws came from or, why we have...
and you say maybe we don't know yet?
Well, I think there's no doubt that the history of science is one of kind of a deeper understanding. As the technology gets better and better, and our ability to measure things gets better, it's why we always want to build bigger telescopes. It's why we want to go into space and use the advantages of being above the atmosphere. It's why we want to use the detectors, which are, electronic detectors like the one in your iPhone, the camera, are 100 times better than the old photographic plates. So, the technology has gotten so much better that we're able to ask and in some cases answer the questions that are, of what the world is and how it works.
Robert Kirshner, thank you very much for your very vivid explanations, and thank you very much for your time.
Thank you. It's fun being here.
Okay, thank you. Thank you very much for watching. You can find this video on dctp.tv. My name is Philip Banse. See you soon with more interviews from the Falling Walls Conference in Berlin 2013. Bye.